All right, so now let's take a look at fluorites and then some of the other structures that are in that table 3.3 in our textbook also. All right, so in the previous example, you saw that lithium sulfide formed into what we call anti-fluorite. And so it's got kind of a funny name because it's called anti-fluorite, but let's look at that real quick. So anti-fluorite fits our schematic really well in that it's again that FCC arrangement of anions. So in this case, the anions can be any version of this, so oxygen or sulfur, but these are the white. So you can see FCC there. And the cations fill up all of those tetrahedral sites. So this is basically the form that you would see that lithium sulfide that you see right here, right? So this is the one we just worked on. And so that's what we define the anti-fluorite. And so it has this stoichiometry where the metal is, there's two metals per anion. And so that's why we have the doubling of the tetrahedral sites, right? Because that gets us to M2X. And so you see examples here. These are very small cations like lithium and sodium, potassium, and then rather large oxygens and so forth. All right, so if we look at the polyhedra then that we see, so we saw that the coordinations from the previous example, so the cation is 4 and then the anion is 8. So if we look at the cation coordination, the tetrahedra, we see that they're sharing those edges, right? So they're sharing these edges in all of these circumstances. All right, so that's the anti-fluorite structure. And I wanted to show you that first because there's also something called fluorite, but this is the opposite. This is if we swap positions between anions and cations. And the reason I wanted to show you the previous one is because anti-fluorite fits with our schematic, and clearly this one will not, right? Because now it's going to have a base of simple cubic with these. So now basically we've swapped, I kept the same image, but swapped the labeling, right? So the anions are now in this simple cubic arrangement, and the cations are in the FCC arrangement. And the reason we do this is we can figure this out by looking at fluorite. Fluorite is the name for calcium fluoride, the mineral. And so if we look at the sizes of calcium in that coordination number, the size is 126, and fluoride, which is the anion, which is usually larger in that coordination, is actually 117. So the cation is actually larger. And so this is why we see the swap. Because again, that rule of anion packing in these close packed arrays is because anions are typically larger. But in this case, we've swapped that. And so we swap the formula, and that's how we get fluorite. So everything's going to be swapped. So instead of M2X, we have MX2. And in this case, all of these deal with very large cations. So calcium, zirconium, uranium, cerium, oxides or fluorides, those all have really large cations, and then the anions are still large, but the cations are slightly larger. So that's kind of what we see with this. And so everything about it is switched. So the coordination numbers are 8 for the cation, 4 for the anion, which is switched. And if we look to the coordination, so in this case we have cubes, and we have edge sharing with those cubes. So in this case, we're still looking at the cation coordination. So in this case, they're cubes. So it looks a little different than those others, but it still shares an edge. And again, they're all really large divalent cations with either fluorides or oxides in those cases. All right, so I wanted to kind of go through the chart that we've just talked about. We've talked about rock salt. We talked about we didn't talk about rutile, so sorry about that. We talked about zinc blende, we talked about anti-fluorite, quartzite, cesium chloride, fluorite. We just talked about. Um, so other binary structures, um, there are other binary structures, but they can also be derivatives of the ones that we see here in the table. And what we see as well in the next section, we're going to look at what we call complex compounds. And so those are where we have multiple cations or multiple anions. And the same thing, they tend to be derivatives of some of these binary compounds, just with added cations that increase the complexity of the structure. But a lot of times you'll see they're based off one of these. And I'll give you an example in that next section.